this point, there are no philosophical implications because we really have not looked. There's no free lunch in the galaxy. The extraterrestrials are not going to make it easy for us.
The Drake equation is a thought-provoking tool used to estimate the potential existence of extraterrestrial civilizations. However, whether the answer leans towards a universe teeming with life or one eerily silent, the implications are undeniably unsettling. In this exploration, we delve into why any solution to the Drake equation can be disconcerting, highlighting the profound questions it raises about our place in the cosmos and the mysteries that surround the search for intelligent life beyond our planet. This is Reveal the Mystery. If you're curious to learn mysteries of the world, space, and beyond, consider subscribing. Let's start with a heads up. If we want to know how likely it is that smart aliens exist in the universe, we need to first think about what we mean by life. On Earth, we have all sorts of living things, from huge trees to tiny bugs. We usually know something is alive because it moves, grows, and does things. Scientists broadly describe life as systems that can eat, digest food, breathe, move around, grow, make more of themselves, and respond to what's happening around them. Basically, they know what's going on, find what they need to grow, and get rid of waste. Some living things are very active, but even plants that seem still can move toward the sun, open up, or grow their roots. However, there are some tricky cases, like viruses. They are so simple that they can't reproduce or eat on their own. Instead, they use cells they infect to do the work. Are viruses alive? Scientists still debate this. So even though there are common things we look for in life on Earth, we have to be careful when defining life. For example, on Earth, water is essential for life. It carries important stuff in our bodies, and if a planet doesn't have water, we worry that it might not support life. But what if aliens could survive using liquid methane instead of water? They might still count as alive. So let's say life is things that look for resources, grow, and make more of themselves, whether they're water-based like us or made from other stuff, or even energy. What's most important is if they could become intelligent and talk to us. To become intelligent, a few things have to happen. They probably need a star to get energy, a suitable planet to live on, competition with other organisms to make them better, and they need to develop problem-solving skills and intelligence to get resources and beat others. Their society must avoid disasters like meteor strikes, earthquakes, or extreme cold, and they must avoid destroying themselves. They have to invest in technology and develop ways to explore the universe. They also need to want to talk to their potential neighbors instead of being alone and send signals to us for long enough for us to notice them. But remember, all of this isn't guaranteed. However, as pointed out by astronomer and astrophysicist Frank Drake during the first SETI meetings in 1961, we can use all these ideas to figure out the chances of us discovering life from other planets. He presented this idea using his famous Drake equation, which might seem complicated, but it's based on a clever and logical concept. Think of it like this. Just as you can figure out how many students are in a school by calculating how many students started each year and how many years they studied, Drake thought we could calculate the number of civilizations in our galaxy whose signals we could detect if we knew the rates of each step in the process. Let's break it down. N is what we want to know, how many alien races are out there for us to find. This helps us understand the chances of discovering them. R asterisk is the rate at which stars suitable for intelligent life are formed each year. Not all stars are right for life, as some are too hot, too cold, or unstable. FP is the fraction of those stars with planets. Ni is the number of those planets in each solar system with the right conditions for life. Planets covered in lava or without the right atmosphere and water aren't likely to have life. FL is the fraction of these planets that can actually support life. FI is the fraction of planets with life that becomes intelligent. FC is the fraction of times that intelligent life advances enough to send out signals. L is the average length of time a civilization exists. By considering various factors, we can attempt to estimate the potential number of alien civilizations we might discover in the night sky. However, there's a caveat. Some of these values remain uncertain. Nonetheless, this uncertainty doesn't deter our pursuit. We can input values that align with current scientific understanding and make educated approximations estimations. Let's delve into what we can reasonably anticipate. Initially, we can establish some fairly confident assessments. Scientists studying the Milky Way galaxy can reasonably predict the annual birth of stars, which falls within a range of 3 to 7 stars. For conservative estimation, let's settle at 5. The fraction of stars with planets, FP, is relatively discernible. Recent Space Telescope observations suggest that a substantial majority of stars possess planets, possibly around 90%. Yet, the count of planets situated at the optimal distance from their stars, with suitable conditions for life akin to ours, is significantly lower. Out of an extensive 100 billion planets within the solar system, approximately 300 million might be conducive to life. For now, we'll exclude highly distinct forms of alien life, as they complicate predictions. This implies a slim probability, around 0.3%, that a planet in a solar system is suitably hospitable for life, Ni equals sign 0.003. This estimate is supported by some evidentiary basis. However, it's at this juncture that complexity arises. When endeavoring to ascertain how frequently life originates, we have only one precedent, Earth. Thus far, we've found no conclusive evidence of life on Mars or Ganymede, despite our conjectures. This dilemma can be examined from two perspectives. One way is to think that life on Earth began as soon as the planet cooled down, which could mean a high value for FL, maybe even a certainty. On the other hand, all life on Earth comes from a common ancestor. Scientists have looked for evidence of separate bacteria, but haven't found any. This could be a coincidence. It might be that life did start multiple times, but the first life was more advanced and outcompeted the new, simple bacteria. This means that life is either very certain or 1 in a million. Let's go with the more pessimistic number, so FL equals sign 0.0001%. We run into the same problem when thinking about how intelligence arises. Many animals show intelligence, like octopuses opening jars, or birds and apes using tools or sign language. This could suggest that life naturally gets smarter over time. But if we look closely, of all the millions of species that existed on Earth, only one, humans, turned out to be smart in the way we want. This makes the odds seem very low. So, let's use the pessimistic 1 in a million value for Fi, or phi equals sign 0.0001%. When it comes to how many civilizations become advanced enough to communicate, this number is likely higher. Even though we only have one species to compare, humans are accidentally sending signals to space. Our industries and transport are changing the air's chemistry, which aliens could notice. Some molecules in our air are there only because of human activities. We also send signals into space with our radio and satellites. Sometimes, we intentionally send messages out into space, like the Arecibo message in 1974. It contained information about us, so any aliens who might hear it could learn about our civilization and history. Although these signals don't travel very far on the cosmic scale before getting mixed with background noise, we still count as a communicating species. So, I'll guess that a high number, let's say 70% of intelligent species, reach this level. The longevity of civilizations is uncertain, as we lack real examples. By spreading to other planets and systems, we increase our survival chances. Using the Drake equation optimistically, there might be no civilizations in our galaxy.